I always think it's fun when a laptop or something doesn't work and you get all the people come up to the front of the podium during a conference to see, if they can get it working. I like to try and estimate the total salary package that's up there. How many millions of dollars of astronomers are there trying to figure out how to get PowerPoint to work. Good use of taxpayers' dollars. Okay, so welcome to part 2 of my lecture, and as Joel said, I have a hands-on this afternoon, and one of the key things that I wanted to do today was to prep you for that and get you in the zone with dealing with the code and understanding what you're going to be doing. We only have an hour and a half, and that may be a long time, it may not be long enough, I don't know, but there's some stuff that's relevant to what I was talking about today that we can focus on today to really get you inside what's going on with building galaxy formation models. So this is about the parameters, right? So how do you build, we talked yesterday about how you build these models, so how do you start to calibrate them and turn them into something useful and physical. So this laser pointer also doesn't work. All right, so before we start, new day, and maybe drinking last night, I don't know. So let's just do a quick recap of what we covered yesterday. We talked about the skeleton and the flesh, how to build a virtual universe. We need the skeleton, we need the flesh. So the skeleton doesn't come from taking real data. I guess if you trace it back far enough, it's built from real data, but we take it from a supercomputer. That's an n-body simulation. We have to assume a cosmological model to run that simulation in order to evolve the universe, the backbone of the universe, the dark matter forward in time. Then on top of that, we couple an analytic model that describes how the baryons evolve within that dark matter background. Okay, and we talked about the different physical prescriptions, the different baryonic reservoirs that we would need in order to build up a universe, and the different physical prescriptions that would transfer mass between those different mass reservoirs. So in particular, hot gas, cold gas, and stars were the 3 main components, but as Mike pointed out, we could have a lot of other baryonic reservoirs if we wanted to. Depends on the level of we wanted to make our model, and also the kinds of observations that we wanted to compare against and try and understand. So this is one example. It's the Millennium Run, of course, and the analytic model that you're gonna, the semi-analytic model that you're gonna run this afternoon gets run on this. A lot of man hours go into calibrating it and making the results look nice. You won't have to do that, or at least not with so much pain and sweat and blood and tears. But when you do that, you can put galaxies in, and this is an example of the distribution of galaxy light within this universe. This is one visualization of a model of galaxy formation. And we talked about how the physics that we put in, and you could equally say the phenomenology, which is what it mostly is. A lot of it's motivated by physics, a lot of it's motivated by phenomenology. Sometimes they're similar things. But what's really important is not whether or not we match the observations, but what we need to do to match the observations, given the model that we've assumed. Okay, so that's really the key here. It's what we need to do. So don't be impressed by someone who stands up and presents a talk where all the lines of their model go through the data. If they don't tell you how they did it, what it meant, what the limitations are, what they learned from it, then it's meaning. And what didn't. The problem is we don't often talk as much about what didn't work because that would take a long time. Long time. So we often get criticized about not showing what's on the cutting room floor, but that cutting room floor is many, kilometers deep. So, in relation to what the questions that you're trying to ask and understand, what worked, what didn't work, what you tried, what's the most simplest thing that anyone would say, let's try this, bang, didn't work. Why didn't it work? What do we need to do to change that? So it's the physical consequences of the model which is really what's important. Money was involved here. Don't forget that. So this afternoon we're going to break into groups. And you're going to have the opportunity to calibrate a model. Despite what you may have heard, some mutterings around, it is possible to do this. And I'm curious to see how far you guys can go Right? It's possible to do. And I'm going to let you not only change the parameters, but change the code as well if you want. If you want to go into that depth, and in a bit I'm going to show you the bits of code where the bits of physics are implemented. So you'll start by changing the parameters and see what it does. But if you decide we really need a redshift dependence on something or whatever, you can do that as well. I understand as well not everyone has the same level of coding ability, so that's a little tougher, and I'm happy to help out if you've got some ideas and you want to see how this is done. But we'll do that this afternoon. So this is kind of where I end up. Semi-analytics are a really simplified version of galaxy formation because you're looking at the evolution of the universe in a cosmological context. And the reason why you're doing that is because we have these massive survey data sets with huge statistics. You can't run that in detail with hydrodynamic simulations. So you need some very fast way to look at the properties of galaxies. So because that's what you're doing, you have to simplify things down to the essence. But we can even go even further than that and strip out basically, most of even that physics and distill it down to an even simpler toy model. And this was the one that Risa talked a little about, the one that I showed at the end, where you have dark matter halos growing in time. These are tracks of dark matter halos. This is redshift here. And you have this band where formation tends to happen. And if you get that right in a galaxy formation model, it turns out you get a lot of the way to reproducing many of the important properties. Things like downsizing and so on fall out. Downsizing is an obvious one in this scenario because massive things will cross over these lines early as they grow, and so their star formation will shut down early. Less massive things will cross over these quenching lines later, and their star formation will shut down later, and so you'll get those things to naturally come out. So it's a nice cartoon picture that we can understand galaxy formation. But I also highlighted at the end of yesterday's talk that the diversity of the population is important. So just having a halo mass and saying this is the mean behavior for the halo mass is not going to be enough when you're comparing with observational data, because within a population there's a huge diversity of histories, of the way things progressed and what was important for that particular object. And again, what's critical is what you're interested in, the question you're asking, the properties you're measuring. You can constrain a population through one property and look at the variation in the other properties, for example. And the nice thing about semi-analytics is that it'll give you those diversities because the diversities come from the growth of the dark matter halos. All right. So this is my slide, similar to Risa's, that I use, and I just want to emphasize this point one more time, that the model is only as good as the questions we ask. Okay? So these are not do-all models. The deceptive thing is that they give you such a richness of information and data back, and you think you can do all, but you can't. Okay? So you have to be really careful, and we'll see a bit more of that later. And an important point here is that for systems with infinite levels of complexity, and I'm going to put galaxies into that category, okay, there's no such thing as a correct model. Okay? So we need to sort of set aside this idea of having a model that's right or matches the data. Matches the data, right? It doesn't mean a whole lot. Usually matches the data means we tuned it that way or we were lucky, right? Because nothing's done from first principles here. Right, so let me give you some examples now of how, at least how I feel you can use these kinds of models to gain some insight into what the observations are presenting to us, where there was otherwise it wasn't really clear what was going on. Do that. Does anyone have any questions? I'm going to start my timer again. Over here. No? Come on, question. Ask a question, because I know you were listening.
How much can this risk go before you consider it not anymore?
I'm trying to think. You're welcome to edit the source code sufficiently so that it does a sham model instead of a semi-analytic, and then it would be your code. Right.
Wait, but was your question for the purpose of winning the prize?
So what we're actually going to do this afternoon, well, it'll be next Monday's lab session when we present the models back. And you'll break into groups, but you'll have to present, as I said yesterday, you'll have to present what you did and why it worked. Okay, that's the key part. Why is what's important, not what. So you'll have to do that, but I actually decided that I won't be the judge, right? I think I'll let everyone judge which is the best model, which one deserves a prize. And it may be that none do because something's really hard and nobody can get it. And then we should all decide that, all right? So if you stand up and present a spectacular model and describe how you did it by rewriting every line of code into a sham, that might be great, but people might feel like they were being changed then. All right, time has started. Get your questions ready. All right, so what can semi-analytics tell us about galaxy formation? Here's just some examples of my own of what I think are great uses of semi-analytics, right? And here's one example, void galaxies. So in 2005, I was working on a project looking at the environments of galaxies in the 2DF Galaxy Redshift Survey. So I'm not going to define environment here and everything, just use your general understanding of what environment means. In this case, it was a large-scale 8 megaparsec environment. And in particular, back then, we wanted to use the power of these large distributions. We had to look at voids. Clusters have been studied to death forever. We wanted to look at voids and void galaxy populations. So we looked at void galaxies in the survey. And what I'm plotting here is the luminosity function. So this is just the abundance of galaxies of a given luminosity as a function of that luminosity. Okay? And these follow typical shapes. Here's a cluster as well from this analysis, and here are the void ones. And I've broken it up into red and blue, early, late types. Okay? And these have different physical, they're in different stages of their evolution. You know, red galaxies tend to be dying or dead. Blue galaxies tend to be alive and star forming. Okay? And you find that blue galaxies dominate in the voids and red galaxies are a subpopulation. Okay? We kind of knew that. Okay? Voids are characterized by blue galaxies. But we found something really interesting, which may not be instantly obvious, is that the brightest galaxies in the 2DF survey showed an equal abundance of red and blue. And it's not totally obvious why that might be. Okay? So if you look into voids, the space density is really low. They're voids after all. But why is there an equal abundance of blue and red galaxies? So dead galaxies and alive galaxies. And this is not just dust. These are selected spectrally, right? Okay, so let's roll out our model and crank the handle and see what that says. So what we do is we don't go and recalibrate and fit and all that. Again, that's not the point. Matching data is not the point. Let's just run the basic model. Same model that we had before. Let's just run that and measure the environments and make the same plot. Now remember, in the model, what makes galaxies red are the AGN, massive galaxies, these bright galaxies. What makes them red are the AGN. That's what we put in. Remember as well, I'm not sure if I actually said this, but there's no environment dependence in how we put that in. Okay, and I'll talk in a little bit more detail about the simple equations we used, but it just kind of depends on the halo mass. Now there's an environment dependence of the halo mass, but we didn't put any explicit environment dependence on the feedback mechanisms or this is that. It's just put in the same for every single galaxy, every single halo in the model. Okay, so we just run this through, and this is what we get. So the lines here are the model, and the data points are the data, right? So this is kind of interesting. It's not a perfect match. Like I said, we didn't do any retuning or calibrating. We just blindly ran the model. Okay, but it goes through the data points, and interestingly, we do get this population of red galaxies in the model. Okay, so that's great, not because we get the population, but because now we can go into the model and ask what's going on. What happened to produce that population? Given that we're putting in AGN to make these galaxies, and we're talking about voids here. And voids are dominated by gas and blue galaxies. All right, so let's go searching through the model. All right, so we'll start by looking at the halo mass function. So this is just the halo mass function of everything. Okay, and that's this line here. I have the whiteboard in the way. You guys will get special attention when I move to the whiteboard here. There's a bit of a bias going on. So this is just the halo mass function of everything. What I said was, let me break this up into halos that host red galaxies at their center and halos that host blue galaxies at their center. At the different halo mass functions for that. And that's what the red and the blue line is. So remember, this is just everything. There's no environment here. And of course, we get the expected result that the most massive halos are hosting those red galaxies, and the lower mass halos are hosting those red galaxies. So I just want to point you to something here, that the transition point where red galaxies tend to dominate, around 10 to the 12, 10 to the 12.5. Okay? So this was the upper line in the plot that I just showed. Trajectories go across, quenching begins, star formation shuts down because of the AGN. That's just reflected here. So let me do the same exercise now, but for the void guys. And let me have a look and see what that looks like. And this is the result, okay, in the model. So you can see the abundance is lower. That's to be expected because we're in voids now. But I want to highlight something here, that where this transition happens is in roughly the same place, okay, in terms of halo mass. Remember I said there was no assumption about environment in terms of how we put the AGN in or how we shut things down. So it's just happening the same in all environments. And if we went to clusters, if we went to filaments, whatever, it would be roughly in the same place for all environments because there was no assumption put in about environment. But let me highlight something. The red guys dominate in the more massive things in voids, and they're a tail above that critical mass. Okay? So where do these red galaxies come from in the 2DF survey? It's the same space density. It's just the tail of the mass function in voids above this critical mass. And if you have halos above this critical mass, AGN will be efficient there and star formation will shut down in their galaxies. The space density is lower because the halo mass function shifts as you go to lower density environments. But as long as you're above that critical mass, the model will shut down star formation in halos that are more massive. Okay? So that's what's happening. At least that's what's happening in the model. Now, this doesn't say that's what's happening in the real universe. This doesn't say that's why there are these bright red galaxies in voids in the 2DF survey. But it makes a prediction that there really shouldn't be anything different about the quenching mechanisms for these red galaxies between voids and clusters in the mean density. And this can be tested. And then this tests the model and the assumptions. Okay? So do I have any questions? That's example one of a way, at least I think it's a useful way to use the models. Not fitting data, but trying to find out why a particular population is there and what could have happened, and then what predictions could be made to test that to see if it's really what's going on. So let me show you another. And this actually comes back to some stuff Joel talked about that I haven't published. You know, who here has papers they wish they had published? I have lots of them. I get depressed every time I go to conferences. And this is an example one. Maybe I should publish it just really quickly. Thank you for that. Yeah, I know. I'm learning to accept it, like my gray hair. All right, so let me show you now, let me talk now about black hole growth mechanisms. All right, because there's this kind of, you know, it was assumed for a long time that quasars are mergers. Right? Who thinks that? Quasars result from the merging of two gas-rich galaxies. You need the, Joel does.
I'm not saying that's the only way.
Yeah, but that's
That is a way.
that's a way, and that's the, except that was the dominant paradigm that people were exploring and discussing for a long time, right? Yeah, and for good reason. Not, you know, it wasn't blindly assumed that. Lots of gas. You need some way to get rid of the angular momentum to get the gas down to feed the black hole. Angular momentum doesn't just disappear on its own. And a great way to do it is to smash things together. And if we got two dinner plates and called them spiral galaxies and smashed them together, you'd find a very significant redistribution of lots of different things. Right? And so smashing galaxies together is one great way to get the gas down to the black hole, and then it feeds it on a short time scale, and bang, you've got your quasar. Makes sense, right? So that's one way. But there's another way. And the other way is through instabilities in the disk. So you'll have a gas disk, stellar disk, and instabilities will form, bars will form, and this is another mechanism through which you can redistribute angular momentum. And when that happens, you might get some star formation, you might get some funneling of gas down to the center. And it's not as violent, typically, as mergers. But it could be a very efficient way to feed a black hole. And this might be a kind of quasar, or at least a kind of active galactic nuclei, an AGN. Right? And so you can test that with these models because we have a model for how quasars turn on. And we can keep everything else fixed and shift out, switch out that model and look at what the consequences are for the population of galaxies that come from making those different assumptions. So let me show you these two different ideas, building black holes through mergers, building black holes through disk instabilities. Okay? See if it makes a difference. Right? And if it does make a difference, then maybe those differences are observable. And we can go and test. And we can say, for this observation, both mechanisms produce the same result. But when we go and break it up this way, we'll get a difference. And the difference is because of blah. Right? When I started this, I was thinking environment is the way to do it. Because you can imagine that mergers have a very different environment dependence than disk instabilities. And so if you look at, say, the fraction of quenched galaxies or the black hole mass function or something like that in different environments, you'll see a difference. That was my intuition when I started this. Right, so here's how we black holes in the current model. This is a simplified version, but basically when there's a merger, some fraction of the cold gas goes onto the black hole. And we modulate that by the merger mass ratio. That's what this MR is here. So that major mergers when the galaxies are of equal mass, it's more significant, right, than minor mergers. Makes sense. Okay, but this is basically it. And this is what we got, what we published for the model. This is pretty much the basic, rough way that everybody does it. Here's our black hole bulge relation. Talked a little bit about this yesterday. And here it is compared to the observations. And these observations might be a little bit old now, but it's pretty much located to these higher masses. And there's still not a whole lot of data points. It's really hard to get black hole masses in an unbiased way. Okay? But, we calibrate the model. This is not a prediction. We calibrated the model to make it look like this. Okay? So, great. But now let's just switch that out. Let's turn it off. So black holes do not grow that way anymore. And when a merger happens, the morphology of the galaxy still changes and all the other things we do. But we comment out the line that says grow black hole. So there's no black hole growth through mergers. And now we'll turn on a model for disk instabilities to grow the black holes. And so what we say is as the stellar disk becomes unstable, and I'll talk a little bit about this later, just a Toomre criteria given the mass and the size of the disk, some fraction of the cold gas will be dragged in and accrete onto the black hole. So it's a very similar model. It's actually a similar coefficient. All right, so that's 0.1. And this is 0.01, this is 0.03. But it's modulated by the merger ratio. And, they're often 3 to 1 or smaller. Right? So the coefficients are of all the same order. And so let's run that now. Okay, so here's what we had before. This is merger-driven growth, and here's disk instability-driven growth. Now, it looks a little bit different, but when you compare it to the observations, it's basically the same result. Okay, so disappointment. Have you ever sat in front of your computer inside? And so that's what happened. So we say, all right, okay, it looks the same in these larger global statistics. We kind of set the parameter anyway, the 0.01, to give us the right normalization. It was where we would have to have put it anyway for it to be. Oh, it's question time. All right, who has a question? Yeah.
Why is the scatter so different?
Yeah, that's a good question. And this way to test in the future as the observations get get better. Different models to grow black holes will give you different scatters, and actually within models, the same even between different semi-analytic codes, the same kind of physical model may give you different scatter just because the other parts of the model are giving different results. So there might be more scatter in the cold gas fraction. When the merger happens, you'll get more scatter in the black hole. And so for our we get a lot of scatter here when mergers grow, when mergers cause black holes to grow. Disk instabilities, there's not as much scatter. So I guess when the disk instabilities are happening, there's not as much scatter in the cold gas in galaxies of a given mass that produce those.
So in the plot on the right, you only have this instabilities and not...
No growth through mergers. Yep. These are extremes. Everything else is the same. Everything else is the same. No parameter changes, nothing. All right. So let's go and test some. Other statistics. So maybe there's some differences surface somewhere. All right. Here's the luminosity function. Now remember that as black holes grow, then we have the AGN shuts down star formation. So we may have the same black hole bulge relation, but maybe where those galaxies, where those black holes are growing and when they're growing, so on, the histories might be a little bit different, and therefore the shutdown of star formation is occurring a little differently. So this is the merger-driven growth. This is the disk instability-driven growth, right? So again, not a whole lot of difference. Okay, let's look at what's next. Environment. So I said this is where I thought there would be a difference. Okay, environment, because you would expect disk instabilities to be happening in different environments than mergers. So here are the mean density, clusters, and voids. So this is basically the same environment measure I showed in the previous example. And now for the disk instabilities. It's kind of a little bit different, but nothing you could sort of say, here's a prediction. All right. So it seems for all intents and purposes that I can produce exactly the same galaxy population through using black hole growth through mergers versus black hole growth through disk instabilities. And physically, these are totally different mechanisms. All right? Now, I don't know whether this is a result or this should be a disappointment. Right? Maybe it's a result to be published because people will look for other ways to test these ideas. I don't know. I felt a bit like this right, when it happened. These are not my children, by the way. My children are much better looking. All right. Okay, so, so there's two examples, right? So one where it was kind of a success, we learned something, there was something clear that came out. We were able to isolate the important factors, it made sense. It may not be right, but it gives us something that we can predict. We can point observers to and say, go and test this idea. If you look at dark matter halos of a fixed mass in voids and dark matter halos of a fixed mass in clusters, you should find very similar populations, because halo mass is what's important, because that's how the quenching's going. Not by environment, but by halo mass. And the differences just come from the different abundances of halo mass, not from any environment-specific physics. So that was the first one. The second one, testing different growth modes of black holes, we got the same answer. So it's hard now to separate out and say, here's a prediction, or this is what you should see. This is maybe a bit of a dead end. Okay? But still a very useful way, because how else would you do this in a statistically meaningful way, in a quick way? Right? There are ways to do it, but this is a nice one. All right, so let's start talking about the down and dirty. I want to shift gears now and start to talk about parameters and code, things like that. So let me first tell you what semi-analytics assume, because you've got to know this, because all your results are interpreted through this lens. Assume that the cosmology is correct, okay? Or at least we assume that we don't say anything about the cosmology. We're at the mercy of the cosmology. Now we can run different simulations with different cosmologies, different dark energy models, for example, and then run the same semi-analytic on those two different dark matter trees and compare the results. That actually would be very interesting, and we're doing that at the moment. But you need those simulations first, okay? We don't, but the model itself doesn't say anything about the cosmology. It also assumes that the correlations extend to all redshifts. So for example, the Kennigan-Schmidt law of star formation. Okay, what's the simplest thing you could do? You just assume that the local relation is true at all times. So star formation that's going on at redshift 10 follows exactly the same prescription as star formation that's going on at redshift 0. Now that might be an absurd thing to do. It probably is. But unless you can give me a prescription for star formation at redshift 10 and tell me how it changes with time to end up at the Kennigan-Schmidt law, we can't do any better. Okay? So we have to make this assumption, and when we interpret our results, if we think our results might be sensitive to something like that, then we have to factor that into the way we interpret things. We also assume the baryon fraction is universal. As I said, to work, we're not actually following baryons. That's the analytic part. The numerical part is all the dark matter. So we're attaching baryons analytically to the dark matter halos, and we have to know how many baryons are associated with any given halo. In the model you'll see, baryons are always conserved. How we work out, as we step down through the time steps of the simulation, how we work out how many new baryons to add at a time step is we sum up all the baryons that are currently associated with that halo and then difference it between the baryon fraction times the new halo mass and the baryons we currently have. Usually that's positive, but sometimes we lose baryons. Sometimes you lose dark matter halo mass, either because of inadequacies in the halo finder, for example, or mergers. Two things come together, stuff gets thrown off, it becomes unbound for a little while before it comes back in, and that will be reflected in the baryons. It may be that the fraction's not universal, it may have a halo mass dependence. Is it 15% in 10 to the 8 solar mass halos? What do you think, Risa? Yeah. So we have to interpret our observation, our model through this, knowing this. Somebody agrees. All right, and the other important thing is that one of the things all models assume is that the halo properties, the galaxy properties can be derived from the halo properties with some appropriate accounting for physics. Now again, that might not be true at some level. There might be halo-independent physics going on, and then you can't just tie it back to the halo mass or the growth or the velocity with some analytic equations. I always thought if God, or whoever God, wrote a semi-analytic model, it would probably be very complicated. But I think he or she could perhaps do it. Insert joke about Simon White here. Okay, so what are we at the mercy of? We've kind of already said a couple of these. We're at the mercy of the initial mass function. So remember the initial function of you standing outside the birthing ward at some hospital and being arrested, right? Measuring the lengths of babies, the initial mass function, how many stars are born per unit star formation episode in different mass bins. And this affects a lot of stuff. Most notably the luminosities and stuff like that, the colors of the galaxies and how they age and the metals and all this sort of stuff to supernova. We have to assume that. Now, we could say that the initial mass function and the stellar population models and so on, stellar population models is number 2 here, they're part of the model and we'll adjust it as part of the model, but they're whole areas of research in themselves. So what we just tend to do is take the expertise from the people in those areas and say, we will use the Bourgeois and Charlot model to build our galaxy luminosities and our spectral energy distributions, or we will use the Mariston 2005 model or something like that. And there's a group of researchers all around the world who are working on that, and they're the experts, and they can advise us. But we have to know that we're at the mercy of that. And if our luminosities are incorrect, it may not be that our model's incorrect. It may just be that our stellar population model's incorrect. So our underlying star formation rates and all that might be fine. And that's why we need to test the models in many different ways. A really important one is the quality of the constraining observations. All too often I see a new set of observations come out, and then people scatter to retune their model so their lines go through these new data points, and then a new set of observations come out and they sort of run to fit that. And you don't want to be publishing a paper every year or 2 years, just chasing the latest observations. Observations don't always get better. Right? Sometimes they get worse, or sometimes they're just different, and it's not clear. And stellar mass functions, they're a classic example of this. When you fold in all the uncertainties and everything, and on the exponential tail and all the things that can go wrong, in some ways it's almost unconstrained, especially at high redshift. Even though the data points you see in the papers, kind of look nice. And that's not a criticism, it's hard work. But we do need to know that we're at the mercy of this, and we shouldn't just be chasing data points. Right? It's important to appreciate this. And as we move into the era of what Risa was talking about, using Monte Carlo Markov chains to calibrate the parameters and try and gain insight that way, the quality of the observations, the errors, and the covariance matrices and all this sort of stuff will become more important. And then as well, there's the quality of the underlying simulation. Okay, so what is the spatial resolution of the simulation? Right, you want to be careful that you're not saying things at a greater level of detail than what you input in the first place. So you have to be careful you're not going down past the mass resolution of the simulation, for example. Oh yeah, I have 10 to the 5 solar mass galaxies in my semi-analytic model, but every particle in the Millennium simulation is 8.6 times 10 to the 8 solar masses. And halos are about 10 to the 10. Halos, you believe, are a few times 10 to the 10. So it's kind of meaningless for talking about galaxies of that mass in my model, even though it produces them, right? So you just have to know this, know that we're at the mercy of them. All right, so in the model that you'll be playing with, it's actually been updated a bit. So there'll be some new stuff in there which you might be curious about. But this is from the 2006 paper. Most of this is still relevant. Here are the main parameters. Okay, I could give a long list of other ones. Pretty much, these are the parameters that matter for the model, where the uncertainties are, where the assumptions are. There's a lot of parameters like sigma 8 and blah, blah, blah. Stuff that's constrained in other ways. And if you wanted to list every single parameter like that and every single assumption, you'd have a long list, but you could probably argue all of them anyway. Most people would agree they're reasonable numbers. So these are where the maybe the contention might be, or where the flexibility to calibrate is. Now, remember, because we're dealing with a system of infinite levels of complexity that we can never capture with a simple model, that these parameters often will need a range because there's lots of stuff we're not accounting for. Okay? And if we want to calibrate the model to match a fixed set of observations, so we can use that as a starting point to explore some other ideas, right, those parameters can be free. At least free within some sensible range if the model that we've implemented has some particular meaning. All right, so let me just go through the important ones. Well, firstly, there's the baryon fraction and reionization. I'm not going to talk about those, although you will run a model with them without reionization to see the difference. Reionization is something that goes on at high redshift. It basically suppresses the infall of baryons into halos. So when I said that we conserve the baryon fraction in halos, so there's always baryon fraction times halo mass of baryons associated with each halo, we can modulate that in low mass systems where reionization is important. Okay? And the other ones at the bottom, I'm going to talk about the middle ones in a minute, but the other ones at the bottom are things to do with metal production and merger times. Okay? So these come from stellar population models and other assumptions about supernova feedback and so on. Right? So I want to focus on star formation efficiency. This is all the stuff we talked about yesterday that's important. Supernova. I think star formation model is kind of well constrained by the observations. Supernova model is totally made up. Right? It's a good guess based on some energetics and so on. I don't think we have good phenomenology for that. So we have to do what's plausible. People will tend to implement a very similar star formation prescription, and supernova can be very different. And again, then we have to understand those differences if we want to compare models. So we have two parameters in our supernova. Basically, how gas gets out of the disk. When supernova goes off, blows cold gas out of the disk. This is going to suppress future episodes of star formation, as we talked about yesterday, so it has a consequence, an impact. But then also in low mass halos, some is going to get blown out of the halo itself, right? The galactic fountain. All right, so we have a parameter that controls how that happens. Right? And then extending that galactic, some of that gas will come back in at a later time. right? And so we have a parameter that governs how efficiently that happens. Okay, and there's a whole lot of ways you can implement this kind of stuff. This is just one way. All right, and then there's the black hole, and there's two main parameters here. It's basically how black holes grow, and the model we're going to deal with, they just grow through mergers. So how much gas gets down when a merger happens. And then the radio mode, so the efficiency when this low luminosity AGN turns on to quench star formation in galaxies. So this upper range that I showed you, as halos grow, the black holes grow, right? Star formation becomes inefficient because you're stopping gas getting into the galaxy. How efficiently does that happen, and where does that happen? So we have a parameter to control that. Okay, so these are the really, what is it, 2, 4, 5, 6 parameters that govern the model that we want to explore and want to understand. All right, so let me emphasize again that the exact value of the parameters, the exact choices are mostly meaningless, right? So if you have a model for star formation, that your star formation efficiency shouldn't be 800%. If it's 800%, there might be something wrong with your model, okay? It should be somewhere between 1 and 10%, right? With a favored value of a few percent now. If your star formation efficiency, as is the case in this model, is 7%, it doesn't mean you have to go back to the drawing board. It means that there's lots of things that you haven't accounted for. There are things that evolved in certain ways, and that's what had to shift in order for you to get these global statistics to come out right. So the exact value is kind of meaningless, and chasing parameter values doesn't tell you anything physical. Okay, that's really important. When you compare relative models, then you might, if you say we had to double or lower the star formation efficiency, we implemented a new model for how gas gets into dwarf galaxies. And in order to bring our global stellar mass function back into line with the observations, we had to halve our star formation efficiency, right? So that tells you something, right? Because gas getting into dwarf galaxies may have some redshift dependence, and then it affects the cycle of supernova feedback, and then you start learning about the process. And what's important there is that you had to make star formation less efficient because you did something else that was probably missing to get that particular population to look better, right? So the relative differences are very valuable to explore. But the absolute numbers, I don't worry too much about, and I don't think you should either. Risa?
So if the absolute values are meaningless.
I said mostly meaningless.
Okay. Well, I'll ask my question anyways.
Yeah.
If the values mostly don't mean anything,
Yep.
then what can we actually infer about the underlying physical process?
I gave you 2 examples, and I didn't talk about parameters at all. And hopefully you still thought there was something to be learnt in that. Questions we ask are the key, what's important. All right. Yeah. And I could give more. I could. There's lots of examples now about. I have a paper on the evolution of. So in this particular model, we found that there was a change, an evolution in the amplitude of the black hole bulge relation, even when we didn't put any evolution into the model, and somehow the amplitude was higher at higher redshift and fell down onto the redshift 0 result. And looking at the model, exploring the model, finding out why that was the case was actually very interesting. And it had nothing to do with parameter values or anything like that. And we learned something. So, and it made a prediction for what you could potentially expect to see at high redshift. So again. Okay. All right. Let's look at some code. All right, so I hope this is going to, I don't want this. I think what I want to do is, I want to bring Gordon up. I feel like I'm talking about an old friend. And actually, I closed this window, but let me hide. Okay. So when you get the model, right, the most important file in there is this parameter file, and basically it contains a host of obvious information, right? So for example, what you're going to name your output files, where you're going to put it, how many files. The tree files are broken up. Right? Full Millennium has 512 tree files. The Millennium has 8. Right? You may not want to run on the entire simulation. The nice thing about this model is you can run on individual trees. So if you're just interested in the most massive clusters, you don't have to search through the simulation. I think you can just run it on those trees and it'll be done very quickly. Where you're going to put stuff. Now this is what you're going to be most interested in. The code options. So there's some options to turn things on and off. And then the parameters. And so we have a number here. Star formation efficiency. Here are the supernova parameters. I probably should turn wrap off. There we go. So it doesn't get confusing. Supernova efficiency reincorporation, right? So these are what I talked about before. This is the cycle, the galactic fountain. Star formation, supernova pushing gas out of the disk, out of the halo, gas coming back in. And then there's the secondary feedback mechanism, which is from H. Right? And actually in the new model, we have a quasar mode now that blows wind out as well, but it blows gas out as well. I'm not going to talk about that. And then there's some other stuff, okay? So let me start on star formation. So the way it's implemented in the kind of simple. So the model that I inherited, so this is a problem, right? That people would put in the simple Kennecott-Schmidt law, and they would say that star formation rate goes as basically how much cold gas is there divided by a dynamical time. So over a time scale, right? So star formation rate is a mass over a time scale. And that's just the Kennecott-Schmidt law, basically, or one form of it. And people would put that in, and when they looked at the cold gas fraction, so remember the star formation rate, the star formation eats up cold gas. So the gas fraction is an important diagnostic of how your star formation prescription is doing. They looked at the cold gas fraction as a function of stellar mass. Normally it should go up. So things that are lower mass are more gas rich in the universe. And it was flat. And so what they did, right, what all models did, is they then parameterized the model additionally. So they parameterized the efficiency. So this is a Kennecott, right, is equal to some parameter times cold times. All right, so that's the Kennecott-Schmidt law, basically. All right, well, that. And so that wasn't a proportional, so alpha. All right, and so what they would say is, well, let's do this. Alpha star formation is actually alpha dash star formation V on V via, just pick a time to some power, right? And all this is doing is saying that the efficiency of star formation changes as a function of the virial velocity of the system or the circular velocity of the galaxy or whatever, right? Some measure of how big the galaxy is. So it kind of sounds reasonable to do that. And this would bring the model back into line with the observations. When you did this, suddenly your lower mass guys were gas rich again, and that's what the observations tell you. And that's important because star formation is the first building block of building a galaxy. So you have to have that kind of right. Now, call this the Kennecott-Schmidt law, right? And it's not really anymore because now they're modifying things. So we actually changed this. We had this idea, or maybe we're missing something here, something wrong. So, of course, star formation doesn't actually just go like this, right? There's a critical threshold, a surface density. So if so star formation happens because you have these big clouds, these big molecular clouds, and they have to collapse. Now, if the surface density of gas is too low, this doesn't tend to happen. And if your clouds aren't collapsing, you don't have star formation. Okay, so in the 2006 paper, we put the equations in. But basically, what we said was that this only happens when you're a critical mass. Right? And we we turn the critical surface density into a critical mass by just assuming a profile for the disk and integrating. Okay. Basically, it's this 3.8 times 10 to the 9. Mass in solar masses is just this times depends on the virial velocity or the circular velocity of the disk, basically. I'm going to use virial velocity and maximum velocity all interchangeably, so just forgive me for that. Times, right? So if you implement that and you just use this prescription, but where the cold gas mass now is just the mass above that critical mass, okay, everything falls into line again, and you get the cold gas fractions to come out right. So this was nice because we didn't have to, in an ad hoc way, over-parameterize the efficiency without sort of a model. And having a Toomre criteria here for the stability of a gas disk and when fragmentation would actually happen, is to me at least a nicer way. And so let me show you where that is in the code. So this is what I kind of want to do. I just want to walk through each part. And then I want to show you where it is in the code so it's not totally unfamiliar. So this is the star formation and feedback bit of the code. Right? This code's still under development, by the way, so you might not look so great or some lines commented out, experimental, something like that. Feel free to uncomment those and go crazy if you think you can understand what's going on. And so this is basically the line. All the coefficients and the units got converted. So this is just the line that determines what that critical mass is. All right? When in a galaxy, when the cold gas gets to that point, then star formation will happen. And so, a very simple thing. So you can see how simple. This is, right? Then a very simple thing. If the mass of cold gas in this galaxy is above that critical line, then here's our alpha. Star formation efficiency is just the mass above that divided by the dynamical time. And the dynamical time here is just the radius of the disk divided by the virial velocity system. Okay? So pretty simple stuff. Okay? I just want you to see what it looks like. Okay. Any questions on? Someone want to ask, why do we only form stars from the cold gas that's above the critical mass and not all the cold gas? Because
I'll ask that. I'll ask that.
Okay, that's a good question. There is no reason other than this is the model we chose. And herein lies the reason why you shouldn't overinterpret the parameter choices. We can still get a good model if we assume all the cold gas. And we could make physical arguments. All right? We don't really know, and this is such a simple model anyway. Turns out it doesn't really matter for the things we're looking at. Now, if you want to look at, if you're going to add to this and put in H1 and H2 gas, and look at high redshift evolution and make predictions for ALMA and all this sort of stuff, this is when it's probably going to matter, and you'll get differences. And then you really want to refine that. But again, we're starting simple. We don't want to go all the way down the levels of complexity, right, if we don't need to. All right. And, the fact that nobody objected when I did this means it's reasonable, probably reasonable anyway, right? And like I said, we argue both ways. All right, so let's talk about supernova feedback. And this is where it does get into where you're just building simple toy models based on your own intuition of how the system works. And I don't think anyone has a real physical model for supernova feedback. The observations certainly don't give us one. So we just assume the simplest thing to get the gas out of the disk. And this is kind of motivated by observations. And it's just what's called a mass loading. So delta M cold to hot. So in the disk, supernova goes off, blows some of that cold gas out. And I showed you an image yesterday of winds being blown and gas getting thrown out of disk galaxies. So some parameter times the star formation rate. Right? And again, we have to parameterize it because we don't know exactly how this works, and we're just assuming one simple relationship for everything. Okay? But we do know that this parameter can't be 1,000. Right? And it can't be 0. Okay? Observationally, the mass loading is difficult to measure, but it's between 1 and 3 perhaps. Okay? And we could make this a function of something if we wanted. Say mass loading has to be different in lower mass systems or higher mass systems, or should have some redshift evolution. Start with the simplest model, but if we wanted to explore the redshift evolution of some that were dependent on something like this, then we would maybe want to run models in parallel and see what difference it makes. And maybe we could make a case based on the metals in the hot component that you need an evolutionary model here to put those out or something like that. We could then make a case, make a prediction, right? But this is what we do. Okay. Now this goes into the halo, right? And it's carrying energy. And so what we argued was that you're dumping energy into the hot gas in the halo. Now we're going to always assume that the halo is in equilibrium, so that might mean that the halo sheds some of its mass to maintain that equilibrium. Okay? So, and I don't have time to work through the equations, although I have them here and they're in the 2006 paper, if you want to look at them. But basically we calculate an energy difference from what you put into the halo, the energy in the supernova itself, and the efficiency with which that's coupled to the gas you're throwing out, and then the energy of the halo, the binding energy of the halo, and there'll be an energy difference. And if there's an excess of energy, if you dump more energy in the halo than it can accommodate, then you're going to shed a certain amount of mass so that you balance those. I don't think I'll write it up. I'll just in the code. So we've formed stars in the model here. Supernova recipe on, yes. Something strange here, hopefully not. We call it reheated mass, so mass out of the disk. That's just that line. So here's that parameter times the amount of stars that were formed. So that's just the mass loading. So that's just that equation that I have up there. And then how much of that actually gets out. It's called ejected gas. And here is the equation. And it looks a little bit more complicated. Let me bring it up. It has 2 parameters in there. So one of the parameters is just the, where is it? Feedback reheating epsilon. That's just this parameter. It's just the mass loading. And then there's an additional parameter that says how efficiently the energy of the supernova is coupling with the gas and how much energy that gas is going to be carrying out into the hot medium. And that's the second parameter. So basically what you want to know is for supernova feedback, there's 2 parameters. One talks about gas getting out of the disk. One talks about gas getting out of the halo. Okay? All right, so that's supernova feedback. And these are the lines where you'll find them. Hopefully the comments are not too bad. So you'll be able to look through here, look through the code. All right, so you've thrown gas out, and you've made some physical argument that you're doing it on the basis that the escape velocity of that gas as it's being pushed out is above the escape velocity of the halo of the system, something like that. But halos are not static, they grow, and so the halo will grow. And at some point, that gas may be captured again. Or the gas that was thrown out as part of that halo might get eaten by something much more massive. And then you have to decide what to do with that ejected gas, because presumably it's just going to be assimilated as well. Okay? So that's the galactic fountain. The galactic fountain is supernova going off, blowing gas out of the disk, out of the halo, and then it raining back down at some later time. So how do you model that, right? How do you capture that behavior? So the way we do it is very simple. We just say that once we put gas into this ejected reservoir to balance the energy budget of the hot halo, that gas will come in on some fraction of the dynamical time. So delta M ejected to hot is equal to some fraction of the mass that's there divided by the dynamical time of the system. And for those who don't know, the dynamical time, the way to approximate the dynamical time is just v_vir on r_vir. So can someone check the units to make sure they're units of time? Okay. So in this case, the system is the halo, so r_vir is appropriate. When we're talking about the disk, it would be the radius of the disk. So it might be vc on r disk. So that's a good back-of-the-envelope way to estimate the dynamical time. And so if this is 1, dynamical time, all the gas comes back. Okay? I think in the model it comes back in 2 to 3 dynamical times. We have to slow down the reincorporation of the gas a little bit in order to get the cooling, then the star formation rates, and so on, that cycle to come out roughly right to give us the correct evolution. All right.
Is that 1 over dynamic time? Is that 1 over dynamic?
So this has units of distance over time, and this is units of distance.
So it's 1 over
Oh, sorry. Okay. Good. So, sorry, r_vir on v_vir. I did that deliberately, of course. Yeah. Okay. Good. All right. Our galactic found. And again, we really don't have a better way to do it, and different models may do this differently, and this is what needs to be explored and compared. How gas comes back into galaxies is very important. Now, one of the things that we could be doing, we should be doing, we are doing, is looking at hydrodynamic simulations of this kind of stuff, right? And looking at how gas comes in there. But it's incredibly complex, and it's hard to come up with a simple relation that approximately captures the behavior of everything. So this is what we tend to stick with. All right, so that's the star formation supernova feedback cycle in the model. The final thing is the black hole growth. So I told you before that black holes grow through merging in this particular model. It's very simple. We just say delta M black hole is equal to some parameter, right? We don't know the efficiency of black hole growth, so we parameterize it, but we hope that the value we need in order to match the observations is reasonable. If it's not, then clearly we're missing something significant. We may be significant anyway, but this is our starting point. So the mass of gas, that's what's accreting. So this is the ratio of galaxies, that's not a mass. So when the merging is very significant, more gas will get down. When it's less significant, less gas will get down. And then we have this thing that you'll see here, which basically calculates the efficiency. And I said before that it's very unsatisfying when you have to sort of add in, reparameterize your efficiencies just to get a particular result without a physical motivation. This is an example of where we do that. It actually comes from an earlier paper by Kaufman and Hanault. Found to get the right slope of the black hole bulge relation, they needed to make the efficiency of black hole growth less efficient in low mass systems. Okay. So there's a couple ways you can look at this. It's a calibration. And matter. Or if you want to explore it physically, then you've got to go into exactly have a better model for black hole accretion and all this sort of stuff. So maybe there's this model which could provide some input here. Just so you know, there's the reincorporation that we just talked about. Reincorporation factor. Here's the dynamical time times dt, right? And this is the ejected mass. So the black hole stuff is in the mergers. Right, so deal with galaxy merger, grow black hole. And this is just this here. So black hole growth. This is the parameter times the mass ratio, and here's the ugliness that I told you about that modulates that efficiency, and then just times the cold gas. Okay, so here's, if you wanted to get adventurous, who has a better black hole growth prescription, right? You can change this one line and rerun the entire model and see what it does. Okay, so there's that, this is the power of this methodology. You can quickly change these assumptions. All right, and then the final thing is the quasar mode. So that's the piece of the AGN, or the black hole puzzle. So once we have black holes, they need to do something. Otherwise, there wasn't point including them for galaxy evolution. So this is what we call the radio mode. And this is what gives the turnover in the stellar mass function that I turned about when I talked about AGN and the quenching of star formation and the suppression of cold gas into the system. This is the equation that does it. We started out when we built this model. Well, let's do the equation first. Right? So the accretion rate onto the black hole, right, in this radio mode. Again, we have a parameter, okay, because some way to modulate the efficiency of this. And it just depends on the black hole mass times the hot gas. So what we were assuming here is that this mode comes from the hot gas accreting onto the black hole, not the cold gas. The quasar mode happens from cold gas getting onto the black hole. And we were arguing that this low luminosity mode, this radio mode, this suppression of star formation mode, comes from the hot gas. So that's why we need the hot gas fraction, because if there's no hot gas there, obviously there's going to be no. And to the virial velocity third. Now, this looks like it was totally pulled out of the air. No, we could argue each point. We could say, well, why not black hole to the cubed, or why not this or that? This actually came from a physical model, and that was where we started. We started with a physical model that, I won't go into the details of it, but basically gave you an accretion rate during this mode. But there was uncertainty about whether this physical model was really real. And when you present a physical model, you can open yourself up to being disproven, which is fine, right? Because that's what we do. But we had tried a bit in other models, and nothing worked. And that physical model worked, right? It gave the right evolution of the massive galaxies, the right colors and luminosities, and all this kind of stuff, right? So to us, at least, we'd found something that worked. We believed that physical model might tell us something, but we weren't sure whether that was actually the right model, or there was another way to interpret the equations. So what we did was we turned it into some phenomenology. We just parameterized it. This is the scaling that gives you the right time evolution of galaxies and halos in the model. Okay, and that's all it is. And then at the end of the paper, we discuss two different models. One of them is that physical model, and there's a second model that results in the same general scaling. Okay, so if you want to actually think about some of the physical reasons why this scaling or scaling like this might work, there's a discussion of it at the end of the paper. But we didn't want to miss the opportunity to present at least a scaling that gives behavior, because up until that point in time, getting that right behavior in these semi-analytic models, stellar mass function, turnover, and so on, had been insanely difficult, and no one had really been able to do it successfully. Now, of course, everybody does it successfully, and there were a number of groups converging on something like this around the same time. All right, so it's 12:30 now, and the next session is the lab. And so this was meant to be a lead-in so that you got to see some of this code. And just for your curiosity, here is that model. It's in the cooling description, because what this AGN does is suppress the cooling. All right, and you can see that we have different models up here, and you can change flags in the parameter file to switch out these different models: Bondi, Hoyle, type accretion, and cold cloud. These are the ones, the physical models I talked about. All right. So hopefully now the code is not, someone's imagination where models just appear. And I actually do encourage you to start with the parameter file and start changing the parameters, but also to go and have a look at where those parameters are used and the kinds of equations that we have in there. And you might disagree with them. Right? You might think there's a better way to do it, or you're missing some important part or something. And that would be wonderful. Add that in yourself, or come and talk to me about it, and we could probably quickly just mock something up and run it and see the difference it makes straight away. So that's an introduction to parameters and code and implementation, the hands-on stuff, what you would actually be doing if you were doing this kind of thing, not just the theory and the end result. So I hope that's given you a little bit of insight into that. And I guess we're gonna, I probably don't need to take questions now unless there are some pressing ones. But when we come back from lunch, we'll start the lab, and I have a Evernote page set up and instructions on how to install the model. It should be very trivial. We'll have a script to run to give you some results back, and we'll start with that point. So unless anyone has any pressing questions, maybe we'll just leave it and break for lunch.